I welcome back all to the course on control system engineering. In this video, we are going to learn the different types of servo motors and the mathematical modeling of DC servo motor. Before going to learn about the mathematical modeling of servo motors and synchros, let me recall what we have discussed in the previous video. We have discussed about the electrical analogous of mechanical systems. That is nothing but we have converted the given mechanical system into the equivalent electrical analogous system using force voltage analogy and force current analogy. Yeah, we'll start with servo motors concept. First, we'll know what is meant by servo motor and why it is used for, and what are the types of servo motors. After that, we'll go for particularly DC servo motor and AC servo motor mathematical modeling. So servo motors are used in automatic control systems. The system is known as servo mechanism when it is used to control the position of an object. The main purpose of the servo motors is to convert an electrical signal applied to the motor to an angular displacement of the shaft. The operation of servo motor is either in a continuous or step motion, which depends on the construction. A variety of servo motors are available for control system applications. The suitability of the motor for particular operation depends on the characteristics of motor and the purpose of the system and its operating conditions. Some features of the servo motor are useful to know to select a particular servo motor for a given application. Those characteristics are linear relationship between speed and electrical control signals. When it is linear relationship, it is very easy to control the servo motor. And also it should have steady state stability and wide range of speed control. Then mechanical characteristics must be linear throughout the speed control range. And also low mechanical and electrical inertia, then it's very smooth to control the position of the object. And also the servo motor should respond at fast. These are the important features of servo motor to select a specific servo motor for a particular application. The servo motors are classified into DC servo motor and AC servo motor based on the voltage supplied to the motor. The DC servo motor has linear characteristics, therefore, the position control in high power applications are also very easy. Whereas the AC servo motors are cheaper and having high efficiency and also has less maintenance requirement, but its characteristics are non-linear. Therefore AC servo motors are not suitable for high power position control applications. Therefore AC servo motors are basically used for low power control applications such as XY recorders, tape recorders, disk drive and printer applications. The DC motors again classified into sliding contact motors with commutator brushes and brushless motor. Here, in sliding contact type, we have permanent magnet motors and magnetic field motors. In the permanent magnet motors, the permanent magnet is placed in place of field winding to provide the magnetic field. In this permanent magnet motors, the permanent magnet motors are economical for power rating up to few kilowatts. But the drawback of the permanent magnet motors is the permanent magnet is demagnetized due to the large current variations. Whereas in magnetic field motor, it is usually economical for above 1 kilowatt, and it is very similar to the conventional DC motor. In the magnetic field motor, the speed and torque is controlled by the armature current or field current. Therefore, the magnetic field motors are again classified into armature control motors and field control motors. In armature control motors, the speed and torque is controlled by the armature current by keeping the field current is constant. Here, the field winding is supplied by the constant DC. Therefore, the field current is constant, and therefore, the speed and torque of the motor is directly proportional to the armature current. Whereas in the field control motors, the armature winding is supplied by the DC current, constant current. Therefore, the armature current is constant and the speed or torque of the motor is directly proportional to the flux produced by the field, where the field flux is directly proportional to the field current. Therefore, by controlling the field current, we can control the speed and torque of the motor. We will see the general working principle of DC servo motor. The basic components in DC servo motor are DC motor, gears, assembly, position sensing device like a potentiometer, and control circuitry. When the supply voltage is applied through the error amplifier to the DC motor, the DC motor keeps on running at a speed, and that speed is fed back to the error amplifier through the gear mechanism by sensing by the potentiometer. Based on the error signal, that means if the error signal is positive, the error amplifier will amplify the error signal and keeps on supplying the voltage to the DC motor to achieve the desired speed, or the error becomes zero. If the error is equal to negative, then the DC motor signal supplied a negative voltage, therefore the rotation will be in opposite direction. By this error signal, we can control the speed of the DC motor. Now we'll see the mathematical modeling of armature controlled DC motor. This is the basic circuit model of armature controlled DC motor. In this, we can observe the field winding is supplied by the constant voltage. Therefore, the current passing through the field winding is constant. Whereas for the armature winding, we have supplied the variable voltage VA. There, the different voltages applied to the motor controls the speed in different ways. We will get the different speeds of the motor. And here the motor winding or the armature winding is the combination of resistor and inductor. When the motor runs, it applies the torque on the mechanical load. There, it produces the angular displacement at the load. Now we'll write the mathematical expression at armature winding. Since the armature winding is the series connection of resistor and inductor, when the voltage applied to the motor, then the armature current passes through RA and LA. In addition to this, we have the back EMF acting on the motor when the variable armature voltage applied to the motor. Therefore, by applying the KVL, we have IA into RA plus LA into DIA by dt plus EB is equal to VA. Since the motor is the motor torque is controlled by the armature current, the torque is in general the torque is a product of flux, the field current and the uh, armature current. Since the field current here is constant, the torque produced by the motor is directly proportional to armature current. Therefore, T is equal to Kt into Ia. If you separate the mechanical part of the motor, we have this model, and if you apply the mathematical expressions on this mechanical system, we have the sum of the opposing torques is equal to the applied torque T. The opposing torques are here due to the momentum of inertia J and due to the dashpot. Therefore, J dt square theta by dt square plus B d theta by dt is equal to T. And also we know that the back EMF is directly proportional to the angular velocity. EB is equal to kb into d theta by dt. And if you apply the Laplace transform on these four equations, we'll get these four equations. The equation 1 is Ia of s into Ra plus La s Ia of s plus Eb of s is equal to Va of s. And second equation is T of s is equal to Kt Ia of s. Third equation is J s square theta of s plus Bs theta of s is equal to T of s. And fourth equation is Eb of s is equal to Kb into s into theta of s. Now in this second and third equation we can equate because of both equations are having T of s, we can equate these two equations. Therefore we will get Kt into I of s is equal to Js square plus Bs of theta of s. Therefore we can write Ia of s is equal to Js square plus Bs by Kt into theta of s. Say this is equation number 5. Now equation 1 can be written as Ra plus S La of Ia of s plus Eb of s is equal to Va of s. Here from the equation 1 we have taken common Ia of s. So it is obtained like equation 6. Now we'll substitute Ia of s from equation 5 into equation 6. Therefore we will get Ra plus S into La into Js square plus Bs by Kt into theta of s is equal to Eb Kbs theta of s is equal to Va of s. Here Eb equation is substituted as Kb into s theta of s. And finally we will get, by taking common theta of s, the last expression is Ra plus S La into Js square plus Bs plus Kb Kts by Kt into theta of s is equal to Va of s. Therefore, to get the transfer function of the armature controlled DC motor, we need to have the ratio of theta of s to Va of s. Therefore, after arranging the last equation into theta of s by Va of s, we'll get Kt by Ra plus S La into Js square plus Bs plus Kb Kts, that is equal to Kt by Ra Js square plus Ra Bs plus La Js cube plus La Bs square plus Kb Kts. Now after taking common s cube terms, s square terms, s terms and constant terms, we will get s into, because in the denominator of the previous expression we have s as a common. From all the terms you can take common s. Therefore s into jla s square plus jra plus bla into s plus bra plus kb kt. Therefore it is equal to theta of s by va of s is equal to kt by jla by s into s square plus jra plus bla by jla into s plus bra plus kb kt by jla. This is obtained by taking common jla from s square terms, because s square terms the first term coefficient must be equal to 1. So we have taken common that jla and taken into the numerator. This is the transfer function of armature controlled DC motor. This armature controlled DC motor transfer function can also be expressed in different standard format. That is, theta of s by v of s is equal to kt by Ra plus s La into j square plus bs plus kb kts. This is what we got in the previous slide. That can be written as in terms of the time constant expression, that is 1 plus st form, by taking common Ra from the first term in the denominator and bs in the second term. Now we'll see how to simplify this to get in the time constant form. Then this equation will become kt by Ra into s La by Ra plus 1 into bs into 1 plus js square by bs plus kb k2 into s. That is equal to, after taking common s from the denominator, we will get kt by Rab divided by s into 1 plus sta into 1 plus stm plus kbkt by Rab, where ta and tm are assumed like ta is equal to La by Ra and tm is equal to j by b. Here it is, La by Ra is equal to ta. That is electrical time constant. Since La and Ra components are belong to electrical terms, and J and B components are belong to mechanical system, so it is a mechanical time constant. So this is the time constant form of the transfer function of armature control DC motor. Now we'll see the mathematical modeling of field control DC motor, and this is the electrical model of the field control DC motor, where the armature voltage kept constant and the field voltage is varying. By the varying of the field voltage, the armature, the motor speed will be controlled. Now we'll see the mathematical expressions of field winding and the motor separately. If we write the mathematical circuit, mathematical equation for the field winding, we have, by the KVL equation, Rf into If plus Lf dIf by dt is equal to Vf. And we know that the torque applied on the motor is directly proportional to the field current due to the armature current constant. We have T is equal to KTF into IF. If we write the mathematical expression for the mechanical construction of motor, we have J d square theta by dt square plus B into d theta by dt is equal to T. Now if we apply the Laplace transform on both sides of the obtained mathematical equations, we will get the first equation Rf If of s plus Lf into s If of s is equal to Vf of s, and second equation is T of s is equal to Ktf If of s. Third equation is Js square theta of s plus B theta of s is equal to T of s. In this equations, second and third equation are having theta of s expression, so we can equate these two equations. Therefore, we will get KTF into IF of s is equal to JS square theta of s plus BS theta of s. And by taking the expression for IF of s, we have s into JS plus B divided by KTF into theta of s. And say this is equation number 4. By From the first equation, by taking common if of s, we have Rf plus Lfs into if of s is equal to Vf of s, and say this is equation number 5. Now we'll substitute equation 4 in fifth equation. Then we will get Rf plus s into Lf into s into Js plus B by Ktf into theta of s is equal to Vf of s. Therefore, theta of S by Vf of S is equal to Ktf by S into Rf plus S into Lf into B plus Sj. That is equal to, now take common SRF from the denominator, we will get KTF by SRF into 1 plus SLF by RF into B. If we take common B from the second term in the denominator, we have B into 1 plus Sj by B. That is equal to Km by S into 1 plus STF into 1 plus STM, where Tf and Tm are the time constants of electrical and mechanical systems respectively, and these are expressed by Tf is equal to Lf by Rf and Tm is equal to J by B, where Km is a constant that is equal to Ktf by Rf into B. And finally, this is the transfer function of field control DC motor. Before concluding, let me recall what we have learned in this video. In this video, we have learned the types of servo motors, that is DC servo motor and AC servo motor. And also we have learned the transfer function derivation of armature control DC servo motor and the transfer function derivation of field control DC servo motor. In the next video, we will learn the mathematical modeling of AC servo motor and synchros. Thank you.